Okay. So when we looked at a spring, we looked at just the pure, where's my spring? The pure force of it. Right? The kind of the, right? How hard am I pushing? How hard am I pulling? But as we begin to look at this in terms of energy, so we looked at it in terms of the kinematics and the mechanics of it, the dynamics of it. Now we're going to look at it from an energetic perspective. So I did some work on the spring, and then if I when I let it go, it does the spring then does some work on something else. It applies a force. It happens over a distance. I'm changing some energy. So that means I need to figure out where does the energy kind of reside? What form is it in? Is it a non-conservative force, or is it a non-conservative work or a conservative work? How does it fit into all of that? Now, I know that some of you have some ideas on where it's going to go, and you're probably right. Your intuition is probably pretty good on it. So we will go from there. So here's my paper. Here's the spring, right? So what I'm going to do is I'm going to have my little spring. Come on. A wonkiness. There we go. Must have gotten involved. So here's my spring. It exists there. So if I grab this spring, and I pull it out to here. Here's my X initial. Here's my X final. There is my delta X. I applied a force on the spring. I know what my force is on my spring over here, because that's how hard the spring is pulling on me. That's going to be K delta X. But that force is changing, is position dependent. So if I were to look at a force on the spring versus delta X, 0, there's no force on the spring. When I pull a little bit, it's a little bit harder. Pull a little bit more, it's a little bit harder. Pull a little bit more, it's a little bit, takes me, now I pull it all the way out there. It's off here, and you'll see that I have a nice line that's on there. Nothing terribly exciting. You already know most of this already. So, oops. What is this? Well, look, I have a force and a delta X. That sounds a whole lot like work. Now I'm going to work is from a calculus perspective. We know that the work is F, right? F dx, F dot dx. This is the, I'm going to leave that there because I'm going to come back to it. But because we really look at it as the magnitude of it, it's F. Let me get rid of that. F dot delta X, right? It's the dot product, which turns into F magnitude of F magnitude of delta X times the cosine of the angle between them. So this is on the spring. I applied it. The force on the spring is that way. The delta X is that way. The theta between those, because F and then the theta between them is 0 degrees. Cosine of 0 degrees is 1. So this turns into work equals F times delta X. However, this F is changing. So we stop thinking of this as It's that maximum F that's out here. That's not how much work I did. Because the amount of work that I did, that I had a changing force. That force is delta X dependent. So then I shift to work is the area under the curve of an F versus delta X graph. So here we go. Oh, look, I want the area under this curve here. Well, this to me looks like a triangle. That area is 1/2 the base times the height. 1/2 the base, which is delta X. What's the height? Well, look, the height is the final, that final force, that is K delta X times K spring constant times delta X. And what do I end up with? 1/2 K delta X squared. That is the work done on the spring. Okie doke. The work done on the spring that is, where did that energy go? That energy went into deforming that spring. So if I let it go, then the spring can do work on an object too. The work done on the spring is equal to the work done by the spring and in the opposite direction. Why does that become an issue? Because it acts just like gravity. This is how gravity works. So that negative of the work done by the spring turns into the potential energy in the spring. Let me now come at it from this way. For those of you who can do a little bit of calculus, work is the integral of f dx. The work done on the work done is f, which is k delta x dx. This turns into k, the integral of delta x dx, which is k 1/2 k delta x squared. Plus your constant, that's your initial work that's on there. All right. So now I have a new potential energy. Let's do a problem. Here's my spring again. It's attached to a wall. I have a box. We'll make it a 2 kilogram box. It's moving this way at 10 meters per second. And it's going to run into this spring. I'm going to put a little pad here. We are frictionless. And the question is, this box will collide with a spring. How far does the spring compress when the box finally stops. Oh, let me rewrite this. How far does the spring compress to stop the box? That's a better question. There we go. Non-conservative work changes the energy. Now, if I wanted to, you could go, right, total work changes the kinetic energy. That's one way to do it. Or you can do it this way. Let's do it this way first, and I'll come back to this one. The spring, because it doesn't really matter, it is not path dependent. So if we go back to here, if I go this way, come over, and then come back down, I still have the same delta X stretch than if I were to go just pull it straight out, or if I were to compress, come over, come off the screen, swing around all the way up to here, come down, go over here, and then come out to there, or extend out over here and then come back to here. It only depends on that final stretch of how much energy is stored in the spring or how much energy has been moved around from the spring's perspective. We know that if friction's in there, right, it's scraping with longer paper, more stuff's coming out. So there's no non-conservative, friction's not there, basically, is how it works. So I end up with 0 equals delta E, 0 equals E final minus E initial. So then E initial equals E final. And now your energy equation is getting quite large. What do I have? I have gravitational potential energy. I have spring potential energy. I have translational kinetic energy, and I have rotational kinetic energy initially. And then gravitational potential energy plus spring potential energy plus translational kinetic energy plus rotational kinetic energy finally. And now I'm going to go through and find what is 0. At the beginning, well, gravitational potential energy, as we're moving horizontally. So we're moving horizontally here. MGH initial, MGH final. So MGH initial. So initially, I'm starting over here at H initial. My spring is 1/2 K delta X. It's not squeezed at all. Its speed is 1/2 mv squared. It's rotating at 1/2 I. It's not rotating. Yay. What about my MGH final? But my H final equals my H initial. So H initial didn't. Now my spring is going to compress by some amount. One half K delta X squared. But I want this, it's sprint, the box slides in, hits this, compresses down, and then I want it to stop. 1/2 m0 squared, right? It's not moving anymore. And then I didn't move far enough over on the paper. 1/2 I or 0 squared. It's not rotating. A quick way to do this would be like, well, okay, it's not rotating. That's not compressed. It stops moving. It's still not rotating. Don't really know what to do with those, but if I put those in there, I subtract this from one side, right, they subtract away. So initially, all of my energy is in kinetic energy, and it turns into spring potential energy. When you are using energy, you build the equation you need to use. Always start here. I end up with 1/2 mv squared equals kx squared. So what if so that's using step 1. What if I do step 2? So number 2, total work is going to give me my change in kinetic energy. So I have work done by gravity, work done by the spring. What else? I think that's all I got. And that's going to change the kinetic energy. That's going to be kinetic energy initial, kinetic energy final minus kinetic energy initial. So the work done by gravity is the force of gravity times delta H, force times distance. Oh no, the distance is whatever that delta X is, times the cosine of the angle between them. Gravity points down, delta X is that way. That's 90 degrees. Cosine of 90 is 0. All right, plus the work done by the spring. Work done by the spring is the force of the spring. Delta X, that's what we did. That's what we did up here. It's a changing force. So you either have to do it in this way or using the area is 1/2 k delta x squared. This is changing times the cosine of the angle between them. The spring's force is this way. The delta X is this way. The cosine between them is 180 degrees. And that's going to equal the final kinetic energy, mv final, which is 0 squared, minus 1/2 mv initial squared. So I end up, this is cosine of 90, this is 0. This thing is 1/2 kx squared times the cosine of 180, which is -1. This is 0 minus 1/2 mv initial squared. So I have -1/2 k delta x squared equals -1/2 mv initial squared. Oh, look, this is the same as that. Well, look, they just flipped. And they even got the right signs. Nice. Oh, I should have probably K final. I totally dropped the rotational. There's no rotational energy flowing around in there. I forgot to put that in there. It's not rotating. There's no rotational energy around. All right, so what do we end up with? What's delta X? Doesn't matter which one I use. So I will use, this one's already here. Delta X squared, the 1/2 goes away. I end up with m v naught squared all over k. Take the root of that. Delta X. Oh, I forgot to put the k of a, I have to come up with a. So here's my k is, I'll make it 1,000 Newton meters per meter. 2 kilograms, 10 meters per second squared all over 1,000. That's going to give me a delta X of. Okay, let's see how we do here. Root. Nope, clear. Second. Root quantity 2 times 10 squared divided by 1,000. 0.45 meters. That's going to be quite the Quite the squeeze. So there you go. So that is where we just have, take the energy, I'm going to go, what if I take this, instead of going this way, I go this way, and now I'm going to go, right? I'm going to put gravity involved. Remember to always watch my process as I'm going through. Let's take this same spring. So the K is 1,000. My mass is 2 kilograms. If we were to do this problem with a ball, but it travel less distance because rotational energy would take play, would I have rotational energy in there? If the ball is rolling, it would depend. It would depend on what happens at the end. Does the ball, because it has energy in, it depends on how much energy it initially had. So it would there's, if the ball was still traveling at 10 meters per second and it was rolling, then you have that kinetic energy of the 1/2 mv squared plus the energy of rolling, and the energy in the rolling would also have to go into the spring. So the spring would have to stop it from rolling as well. So it would get more compressed if it was moving at the same speed versus sliding. Does that make sense? Kind of, sort of. We'll come back to it. Stopping something rolling is a little more complex. We'll get to that in a second. That's a good. Here's your. You know, would the energy be distributed? Well, no. You're staying. If this is still moving it, if it still has a translational kinetic energy, a translational speed of 10 meters per second, and it was rolling, then I don't just have. I have more energy at the beginning. Sorry. I have more energy on this side that then the spring would have to absorb. If I'm getting to where it stops. If I have a rolling ball, it has this and this. If the ball had the same amount of total energy, it would be moving less, but the sum of these two would be the same. All right, here we go. So this initial block is 0. It's dropped from rest. It's from the top. It's from the top. How far will the block fall before it stops? No friction. 0 equals the change in energy. Change in energy is E final minus E initial. E initial equals E final. Gravitational potential energy, spring potential energy, translational kinetic energy plus rotational kinetic energy. Initially. Gravitational plus then string bender 2kr final. Initially is going to be right here. Finally is going to be down here. Initially, it's at some H initial and G H initial. The spring, however, is unstretched. So I'll break that in there since this is our first time going through it. Plus 1/2 m0 squared plus 1/2 I over 0 squared. It's not compressed. Spring is not compressed. There's no energy already stored in there. It's not moving and it's not rotating. MGH final. Here's my H final. But now 1/2 K delta X. There is a delta X here. Plus 1/2 m0 squared. It's not moving and it's not rotating. What am I left with? H initial equals mg H final plus 1/2 K delta X 0. Mg H initial minus mg H final equals 1/2 K delta X squared. Mg H initial minus H final equals 1/2 K delta X squared. Take a look at this. What do I know about H initial minus H final? It is the same as delta X. That is how much the spring is stretched. G delta X equals 1/2 K delta X squared. Two mg divided by K equals delta X. So what do I got? I got 2. Mass was 2 kilograms. G is 9.8. K is 1,000 is going to be delta X. This is how much it gets stretched when you let go. This is not how much it gets stretched when you just put the object on. So 2 times 9.8 divided by 1,000. 0.0392. About that far. All right. Let me go back to that other question where I said, what if it was rotating? I'm not going to solve it, but I am going to set it up. Here's a sphere, same mass, 2 kilograms, rolling. They'll have a little nub here, and as this rolls and goes into there, this little nub on either side is going to catch it. V is going to be the same 10 rolling without slipping, 10 meters per second going that way. Now, how much will the spring compress? I'll do some shortcuts here just because I'm starting to run out of time. Non-conservative work is going to change the energy. That's not there. E initial equals E final. E initial, spring translational plus rotational. That's going to equal gravitational plus spring plus KT plus rotational. This is initial. This is final. Those two are the same. It's not compressed. I want it to stop. So I have 1/2 mv squared plus 1/2 I omega squared equals 1/2 k delta x squared. So this thing rolling at 10 meters per second, I know that omega is v over r, and I know that the moment of inertia is 2/5 mr squared, 1/2 mv squared plus 1/2 2/5 mr squared times v squared over r squared equal 1/2 k delta x squared. So before, you just had this much kinetic energy getting squished into here, but now because it's also rolling, so there is extra energy. It's going to get compressed more. Delta x will be larger. If we flip this around, where I have a compressed spring, it's going to push on a sphere where the initial speed here is 0, and then it pushes it, and now the sphere is rolling. Yeah, then the energy will be distributed between the kinetic energy and between the two kinetic energies. But in this situation where they have a rolling sphere in, the spring has to do a couple things. It has to stop the kinetic energy and also the rotate. It has to stop both kinetic energies, not just the linear one.